Hey there, sixth graders. In this video today, we're going to go through the next part of our notes on non-contact forces. So before we begin, you need to make sure you have the document open. We're still continuing the same doc that we used over the last, I guess, 2 weeks. So it's those non-contact forces guided notes 2021 is the title of the doc. If you don't have that open yet, pause the video and open that doc, find it in your drive and open it up. On that doc, you'll notice that about halfway through, I put a line across, and that separated week 1 from week 2. And we are all done with week 1. That grade went into Infinite Campus. If you were missing any parts of those, you want to make sure you go back, find the videos, get those done. You can then email me to tell me that you went back and finished them, and I will give you some of those points back. For week 2 here, we're going to start with magnets and magnetic force for this video, and then we'll finish it up over the next couple of classes. So again, if you don't have the doc open it up, pause it if you need to, but we are moving on because the slide I have up there right now is the one that we finished last week, which was about weight and mass as we were talking about gravitational force. So magnetic force. In class, we had the opportunity to observe magnetic fields using iron filings and magnets. And so I'll talk back about that lab a little bit. Even if we didn't finish it in one of your class periods, because it kind of depended on which class you were in, you got to see at least part of it. And so it should kind of make sense, and you should be able to make the connections from the lab to what we're talking about here in the notes. All right, so first bullet point that you're typing in is that magnetic fields exist around magnetic objects. And so they are exerting this force. And remember, just like the 2 other non-contact forces, they exert this force on objects when those objects are within their field, right? That field, that region or area of influence. And so that's true also for magnets and magnetic force. It's important to kind of recognize what's happening. Now, one of the things that we don't see when we do our magnetic field lab and we use the iron filings is that we can't necessarily tell the directions of the field lines. The same thing was true a little bit with the electrical field lab, but we got to see it a little bit better because it was a sim. And so they were using arrows. And they showed, if you remember with those arrows, they showed that the arrows were pointing towards the negative charges and away from the positive charges. Well, the same thing sort of exists here with magnetic force. And that's that the field lines point away from the north pole of a magnet and towards the south pole. So if you look up here, where I'm moving my cursor here, this top picture shows those field lines and how the magnetic field is working. Next bullet point is the opposite end of the magnet pointing towards the south pole. In our lab, our magnets were not polarized quite like this picture is here, right? They were split down the middle. So on one side of the magnet, it was the north pole of the magnet, and on the other half, it was the south pole. So it was split. These are split more vertically, and ours was more split horizontally, if you remember. But the same thing still happens. Magnetic field lines pull away from the north, go towards the south. The strength of the magnetic field decreases rapidly with increasing distance. We have seen this and heard this throughout this unit so far. As you get further away from these objects that are exerting the non-contact force, as you move away farther, the strength becomes weaker. So that is something that is true. It is a characteristic of all 3 non-contact forces that we've looked at. That's important to remember, that they share that characteristic. And the same thing happens. Okay, if you remember your gravitational sim lab, the second graph that you did was graphing the same thing with the gravitational force. It was graphing how distance affected the gravitational field. And we saw that it decreased rapidly at the beginning. It was a very steep line at the beginning, and then it kind of flattened out, right? It still was decreasing, but it was decreasing less at the end. And so in math, we define that or describe that graph as decreasing at a decreasing rate, right? So it increases rapidly at the beginning, and it becomes less and less as you move further and further away, even though it's still decreasing as you move further away. And eventually, you are outside of the field, and you're not affected by the magnet anymore. If you look at the magnetic field drawing that I have down here underneath me, right close to the magnet, you're going to notice a lot more of these little iron filings here. It's stronger right there, right? It's stronger right at the ends of those magnets where the poles are. This picture here, we don't see anything further away, but once we get, if the picture was kind of zoomed out a little bit, you would see that there would be less iron filings kind of sprinkled throughout because they weren't as affected as much, right? Because as you move further away, the field becomes weaker. Earth's magnetic field. So now you're moving to the next part of your notes. Well, Earth has a magnetic field. That's important. It was really important at the time when there were all kinds of people looking and exploring, right? The explorers that you might have learned about in social studies class. They were using compasses. Compasses work because of the magnetic field. That was a huge, huge part of people knowing where they were going. Now, here's what a lot of people don't know. And that's that our magnetic poles do not match with our geographical poles. So we know that up towards the top of the planet is the North Pole. This guy named Santa Claus is supposed to live up there, right? The North Pole. But when we are looking at the magnetic field, up at the top of our planet is not the magnetic north. It's actually the magnetic South Pole. So look at the picture underneath me here. Notice that here with the magnet here that they're trying to show you on Earth, S is up here at the top, and that all the field lines are pointing to up at the top because our magnetic north is actually at the bottom of the planet, and our magnetic south is up at the top. So even though we call it the North Pole geographically, it's the South Pole magnetically. And that's usually a misconception. People don't know that. Okay? So if the South Pole of the magnet is up at the top, the magnetic north is down at the bottom of our planet. And this is how a magnetic compass works then. The magnetic South Pole of Earth is going to attract the north side of the compass magnet so that the arrow points north. Because, like we saw in our lab, opposites attract. So if the magnetic south is up towards the top of the planet and you have a magnet inside of your compass, the pole that's going to be attracted is the opposite. So if south's up at the top, the north pole of the magnet in the compass is going to be attracted, which then means the compass would point north, right? So that's why it's opposite, because opposites attract. But yet people don't really realize that. They think, oh, North Pole, it's up at the top. True for geography, not true for the magnetic north, okay? Or for the magnetic field. So that gets to our two variables that affect the magnetic field, right? The two variables that affect the magnetic field, again, are distance, like we just talked about last slide, and that's true for all of them. And then also whether or not you have like poles or opposite poles. And this is just very similar to the electric field. which is why the second half of the notes that we'll do next week or in the next couple classes is going to now look at the connection between magnets and electricity, because they are very closely related. They are intertwined, in fact. And we see pretty much the same characteristics that we saw when we studied electrical force at the beginning of the unit, we are now seeing again here with magnetic force. Electrical force, we talked about opposites attracting, like charges repelling. So if you had two positives, they repelled, two negatives, they repelled. Magnets, opposite poles, they attract. If you have like poles, like two north poles, they repel, two south poles, they repel. And it's not a coincidence that they share those characteristics, because electricity and magnetism is intertwined. And we'll talk about that in the next set of notes. So this ends the notes today. Make sure that you have that part done. Do not hit the turn-in button still, because you still have the second part of this to do in the next couple classes. Thanks for watching, and I will see you next time in class. Have a good day.